Hey folks, welcome back. In this video we're going to look at our first application of interference by division of amplitude, which is thin films. So let's get into it. So we're looking at interference by division of amplitude, and our first application is thin films. It says here that liquids which are less dense than water will form a thin film on the water surface. The colours seen from reflected light, such as those from petrol and water, are created by interference due to division of amplitude. And here's an example of what I mean, and it's something you've probably seen before on like a road surface. So we've technically got three materials here. We've got air above the thin film, we've then got this thin film of petrol over a water surface. So we've got air, petrol, the thin film, and water. And you can see the nice pattern of colours produced there, and we're going to explain how we get this. It then says, consider a ray of light instant on a film of petrol floating on the surface of water as shown below. And you should note here that the refractive index of the petrol is greater than the refractive index of the water, which we know in turn is greater than the refractive index of air. So if we look at the picture here, we've got our air, which is a refractive index of 1, then our thin film of petrol, which has a refractive index of 1.4, and then our water, which has a refractive index of 1.33. So you can see we're increasing in refractive index from here to here, but then we're decreasing in refractive index from the film to the water. And the picture shows that you've got instant light coming in, being reflected, and then being transmitted, reflected again, and we're also told that the thin film has a thickness or width d, and a portion of the light will also be transmitted through into the water from the petrol. It then says the light will be partially reflected from the petrol surface, which is labelled R1 here. So there's the light which is partially reflected from the thin film surface, so that's R1, and it says that this will have a phase change of pi radians since the ray is travelling into a medium with a higher refractive index. So what we're doing here is using what we looked at in the previous theory video for interference by division of amplitude, where we looked at phase change on reflection. So because the light's going from a less dense medium to a more dense medium, when it reflects, that ray R1 is going to undergo a phase change of pi radians. It then says the ray passing through the oil film is then partially reflected from the water surface, which we can label R2. There is no change of phase for this ray since the ray is travelling into a medium with a lower refractive index. So there's our ray R2, which has travelled further than ray R1 because this ray has been transmitted through the film surface and back up, and then it's coming back into the air again parallel to ray R1. And we can say that ray R2 is not going to undergo a phase change of pi radians on reflection at this surface because it's going from a more dense medium to a less dense medium, i.e. the petrol to the water. And we know that from the refractive index because the higher the refractive index, the more dense the material. So we can then say the rays R1 and R2 will now combine to produce interference. So you've got this ray R1 which has travelled a shorter distance than ray R2, and R1 has undergone a pi phase change, whereas R2 has not undergone a phase change but it has travelled further. So what we can then do is say that the optical path difference between R1 and R2 will be 2 times n petrol d. And that's because if we look at the picture here, remember the optical path length will be from the refractive index times the geometric path length. So the geometric path length is basically just the width of my film here, which has the symbol d, and the optical path length is going to be n times that. And we have the refractive index for our film here, which is petrol. So we can say the optical path length will be n petrol times d, but notice how ray R2 is travelling down the distance d and then back up the distance d. So it's travelling a total distance of 2 times d. So that means the optical path difference between rays R1 and R2 will be 2n petrol times d because we've got this factor of 2 difference between the distance travelled there. It then says, however, R1 undergoes a phase change whilst R2 does not. Thus the optical path difference will be 2 times n petrol d plus lambda over 2. So all we're doing is taking our optical path difference from above and we're adding half a wavelength on. Now the reason we can do this is because we know that ray R1 undergoes the pi phase change but R2 doesn't, and remember a pi phase change is the same as 2 waves being half a cycle out of phase or half a wavelength out of phase. And that is where this half a wavelength factor comes from. So the optical path difference between rays R1 and R2 is 2n petrol d plus lambda over 2. It then says, thus, if the optical path difference is equal to a whole number of wavelengths, there will be constructive interference, and if it is equal to a half integer number of wavelengths, then there will be destructive interference. And we saw this in the theory video for interference by division of amplitude. So just a reminder that this is what we saw in that theory video. The optical path difference equals m lambda, where m is an integer, for a maximum, and for a minimum, optical path difference equals m plus a half lambda, where m is an integer. So we can say that for minima, we have optical path difference equals m plus a half lambda, and therefore if we substitute in our expression for optical path difference from above, we have 2n petrol d plus lambda over 2 is is equal to m plus a half lambda. And we can then simplify this because if you expand the right hand side, you get m lambda plus lambda over 2. And that means we have a plus lambda over 2 on this side and a plus lambda over 2 on this side, which could just cancel out. So we end up with this simplified expression, 2n petrol d equals m lambda. But it says here the above relationship was derived for the case of petrol being the thin film, but in general for destructive interference we can write 2n film d equals m lambda, where we've just replaced the subscript petrol for film. And it says here, note, this equation is not given on the relationship sheet but is useful to remember. So it's very much worth remembering this one equation for thin films, that for destructive interference you have 2n film d equals m lambda. And that means that for constructive interference, you would write 2n film d equals m plus a half lambda. And this is perhaps slightly confusing because we usually associate maxima or points of constructive interference with this m lambda factor, but here we're saying it's the opposite. The constructive interference equation would have m plus a half lambda, and the one we derived here for destructive interference is just m lambda. Now I should point out that this derivation is not examinable. You won't be asked to do this in the exam, but it is worth remembering this equation for destructive interference and being able to use it. Lastly, it says the colour of the reflected light from a thin film will depend on which wavelengths, i.e. colours, produce interference, which in turn depends on the thickness of the film D. As this will vary, a range of colours will be observed, as shown below. So these colours are produced because of the variation in the thickness of the film across the water surface. So it's not going to be a constant thickness D like the one we assumed in the derivation. That's all for this video, folks. Thanks for watching. If you made it to the end, I really appreciate it. Make sure to give the video one of these, subscribe to the channel, and I'll see you in the next one. Take care.